Well, hello, Jessica. I hope you're all right. I did receive your message, of course, and I'm glad no one was hurt. Um, it is a pain to get into these kinds of things. We're going to go ahead and get started on this week's material. I'm going to use some of the material from the textbook, the mainly the Triola book, the Vital Source ebook. This will be um, an interesting kind of class for the two of us at this point. Kyle is out for the mod. He got some very bad news about his mother and is on his way to Utah. You may, if you happen to be a person who prays, say some prayers for Kyle and his mother. He's he's very, very distressed. It's just going to be you and me, my dear, for the rest of the mod. So let's go ahead and get started on this. I'm probably going to try and talk for at least an hour and a half, maybe more. Then at the time we would normally go into power hour, I'll cut the lecture off and let you get started on this week's work. So let's take a look first at what this week's work is about. We are looking at, in terms of the material we're studying, we're looking at measures of center, meaning the center of data sets, and we'll be looking at other ways of describing data. This is part of what we call descriptive statistics. This is the part of statistics where we accumulate data, we present it, we do analysis of the data to determine a variety of parameters, such as the center of the data set. And we'll go through several of those kind of measures. Here, the reading for this week will include the open source OpenStax book, chapters 2, 4, and 6, which cover such things as that. We're going to look at standard deviation and bias. These videos I will let you watch on your own. They're Khan Academy videos, which can give you a lot of information. Excuse me, about some of the topics we're going to be discussing and beginning to discuss this week and discuss several times over the rest of the course. Standard deviation is one of those. Standard deviation is a measure of spread of data. We talked a little about the fact that data can be compact or it can be spread out. And compact data sets have smaller standard deviations. Spread out data sets have more, have broader, larger standard deviation values. So it's a measure of spread. Are you on? No. Okay. I was hoping. I don't know why the thing was doing that. Oh yeah. At 6:30, I'll probably walk into the library, and you can we'll record what Katie has to say about the beginning of the mod announcements. So that'll be in about 15 minutes. So anyway. What we're doing, as I said this week, is looking at that. And we're looking at the mean, median, and mode. Mean is a term that really is an alternative term for what we normally call average. Average is, and we don't like to use that term in statistics, although the statistical functions in Excel make use of the term average. but mean is what we use in statistics. And mean is simply the arithmetic average. So we'll go through some of those things as well. This week's discussion, and since there's basically just going to be you and me, we'll carry on the same way that we did last week with the discussions. I've already posted my first posting. You can post, I'll respond, and we can carry that on. But we're going to cover, this is about central tendency. So after we talk about these measures of the center, your choice here is going to be looking at which of those measures would be appropriate for one of these four scenarios. So you'll get onto that as soon as you can. In-class activity, we'll worry about that on Thursday. The assignment this week, again, has the usual Word doc and a data sheet. The assignment, we'll call this one up right now, and we'll see if we can get that to display itself appropriately. And let's see if I can share this. Is it on here or not? Yeah, we'll go here. I think that's right. Yeah, okay. What you have is you're going to look at some information out of the data that's on the spreadsheet. You're going to be doing some calculations, not for all the data sets necessarily, but you're going to be doing some for any one, and then for some of them you'll be doing for all three. Then you'll calculate standard normal distribution. You'll look at that. Excuse me. And this will depend on some material that we'll go over in more detail when you're here on Thursday, because we're really using this normal distribution to find probabilities as well. So we'll get to that on Thursday. Meanwhile, tonight we will be dealing mainly with the standard deviation and with mean, mode, median, etc. So you will be you'll find all this material will be covered in all of these things here. Plus, you'll be discussing some data analysis. Let's go and take a look now at the spreadsheet. Come back here, and we'll bring up the data, the spreadsheet. Okay, we'll open it with there. Bring that up gradually. Okay, so this is the data set. As soon as I get it shared. Okay, so here's the data set, and you can have pulled that up yourself. And it really is, it's out of a doctor's office. We have our client names, we have ages, we have wait times, and then we have a satisfaction score on a scale of 1 to 5. Note that there are some pretty big numbers in the wait times. So we'll discuss things called outliers between now and Thursday. So let's go back now to the assignment. Okay, and we'll go back into here. And again, there is, as usual, an assessment. So you'll have, so again, it's a fairly straightforward week in terms of what we're doing. So let's now go to the Triola book, which is what I will use for a lot of our conversation. And we'll go now to chapter 3 and we'll start off looking at some of these data. Let's back up. So we're going to be looking at something that sounds kind of trivial, but they're good examples of how we do a lot of statistical analysis. Here, we're looking at the number of chocolate chips in different brands of cookies. Now, there are 3 different Chips Ahoy brand: regular, chewy, reduced fat. There's Keebler, and there's something called Hannaford. So there's differing numbers here. We've got 40 samples of Chips Ahoy and Chips Ahoy reduced fat, and 32 examples of the chewy, 36 examples of Keebler, and 26 examples of Hannaford cookies. These are not matched pairs, they're just different samples of different cookies. So we have a range. So there's several things we'll be talking about here. The range, which is basically the highest number in a data set and the lowest number of the data set. So the difference between them is the range. There is the mean, which is the simple average. If you added all of these up and divided by the number of samples, you'd get the average. There's the median, which is if you line things up in order from lowest to highest or highest to lowest, it's the value directly in the middle. If the middle of the data set falls between 2 values, which it will if the data set has an even number of data points, then, hey Joel, then you add them together and take the average of those 2. So we have all of those different those ways of looking at it. There's something called a mode. The mode is simply the data point that appears the greatest number of times in the data set. And there can be more than one mode, but they have to be exactly the same number. So you cannot say you have 2 different modes if one is, say, 25 and the other is 22. They have to both be the same number of appearances. So it'd be like looking at the Twin Peaks, the same height if you graphed things out. So here we have those. So we're going to be looking at those and looking at a couple of things. And one thing to note is that if we look at some of these cookies, some of them, turns out, the Hannaford, for example, they were substantially larger than the other brands. So, and one of the things here, again, let's look at sampling. They do not include the weights of the chocolate chips. So if we're looking at just numbers of chocolate chips, it doesn't tell us about the size. And if you look in the store, you've got mini chocolate chips, and you've got bigger chocolate chips, you've got chocolate chunks, and you've got chocolate chips that sort of look like Hershey's Kisses. They're so big. So, there's nothing in here about that. So it's not clear that this is a great sample, but to make it worse, the guy that did all this work they used all the cookies in only one package from each of these brands. If you were really doing this for purposes of QA, which is the reason you'd want to do this, then what you would find is that you would want to sample from dear. Okay, I'm going to pause this recording. We appear to be having a drill. Well, you missed the fire drill, and then they didn't unlock our hallway, so I couldn't haul this into Katie's announcements, but basically she wanted to, you probably were on campus last night, so, but basically she was announcing that this was the last mod of the year, and she, it's just me. And she was encouraging people to get their work done before the 20th so that they could have the 2 weeks off. Anyway, let's go back to this. So we're talking about chocolate chip cookies and sampling. So sampling here wouldn't be what someone wanted to do for QA purposes. The QA purposes, you would have a much broader set of samples rather than simply one bag. So let's just keep on now and move over to some of the ways of representing the data. This is what we call a dot plot, which basically is just a vertical line with numbers, just cardinal numbers, and then a horizontal line with listing how many cookies were at each of these levels. So in this Hanford, we've got 4 cookies with 15 chips in each. And we have 6 cookies that had 14 chips, etc., all the way down here to a low of 9 and a high of what looks like 21. And maybe it was 22. Yeah, probably 22. But in these others, what we have is a much broader set of distributions. So what we have here is a fairly narrow data set. And like this one here, the reduced fat, are a very broad data set. We've got data points ranging from what appears to be 12 to 28 or so chocolate chips. Note that what all these dots represent is there is a dot for each cookie that has this number of chocolate chips. This kind of a dot plot allows us to go back and visually find out the mode. Remember the mode I mentioned earlier? The mode is the value, the data value that appears the most times in the data set. So for this Hannaford, the mode would be 14 chips. That's the mode. However, we go up here to the regular Chips Ahoy, and we have what looks to be 23 and 25 that have the same number of chips, and they each have, it looks like, 23 and 25. So they got 7 cookies each out of this package that have either 23 or 25. So this is a bimodal distribution. In other words, there are 2 modes, 2 of the same number. So the rest of these have a single mode. And it's different for each one. There's obviously here at 20 for the chewy and the reduced fat, but over here it's 30 is in the Keebler. But again, we don't know what that means. And this is where, when you start seeing statistics, you start asking questions. Question number one, how did you sample? Well, we know they sampled by a lazy way. Obviously they just went to the store and bought a package of cookies, broke it open, crumbled up the cookies and crumbled up each cookie and counted the number of chocolate chips. It's a great way to eat only the chocolate chips and not the cookie, by the way. But the other thing is that we don't have any idea here in this data set as to the size of the chocolate chips, the size of the cookie, or any other thing. Now we know that the Chips Ahoy are all pretty much the same size. Can't speak for Keeblers or Hannaford. I have not seen a Hannaford cookie, so I have no idea. But the issue is fewer chocolate chips implies a possibility that they're larger. More chocolate chips may imply that the chips themselves are smaller. We just don't know. But if we're just looking at numbers of chocolate chips, if that has any meaning to us, then that's what we've got. So there's a concept here is that we also, want to just say, okay, what is the sort of, what can we normally expect to see? And again, we have narrow ranges, excuse me. Oh, sorry about that. We have a narrow range of tall, stacks of dots here in the Keebler. And then there's, just sort of scattershot after that. We have a much smaller range here in the Chips Ahoy, the regular ones. But it's still a range that goes from about 19 to about 29 or 28. So there's still a range here. So we are looking at various measures. We want to look at the when we're looking at comparing and exploring data sets, we want to look at the center of the data set. How big on the quote average is it going to be? How does it vary? How does it distribute? Is it skewed toward one end or the other? If we go back over here, things seem to be fairly well distributed around the center. This one may be viewed as slightly skewed, but pretty much we see that they're distributed relatively evenly. I say that because for small data sets, you're not going to get a really even distribution. Our standard bell-shaped curve, you're just not going to get it. So what we're talking about, the whole process of descriptive statistics is they describe the characteristics of the data set. Inferential statistics is used to make generalizations to populations. Inferential statistics are the goal of all political statistics, of trying to draw an inference as to the results of say, an election. So we want to look at the centers. There are some basic concepts. The measure of center is some value that's at the center or middle of a data set. So we have a couple of these things. We have a mean. In statistics, we refer to the arithmetic mean, which is what most people call the average. Important properties of a mean means that if we draw varying data sets from the same population, the mean generally speaking, in the same population isn't going to vary very greatly. The mean of the set uses every single data value. And there is a disadvantage, a data value that is way away from that mean, either way above or way below. If it's not counterbalanced by something of an equivalent value in the other direction, will actually move that mean toward that data value. We call that skewing. But it also means that the mean is not resistant to changes from those extremes, and we'll get to that later. The notation of the mean is, and how we set this up mathematically, it is the sum, this big Greek letter here, the uppercase sigma, is called the sum of in mathematics, and it's the sum of x being the data value, each data value itself. And from that we can draw our data. And n is the number of data values. So you know how to take an average. You just add them all up, divide by the number of data points. So a couple of things. Okay, what do we got here? Excuse me while I take a look at what I'm being told. Oh, okay, forget it. Sorry about that. If we look, remember we had a population and we had a sample of the population. We have a census, which is the entire population, or a sample, which is a subset of that population. And so when we are looking at the mean of a subset, we denote that by putting a bar over x. This is the value, that is the mean. The value, and the x, in this case, we're talking about the value of a member of the data set that we're taking, and it may or may not correspond to an exact value in the data set. So we specify that as x bar. If we're looking at the entire population, the mean is denoted by mu. A word about population. In a large population, we expect to see a normal distribution of data. Let's take a look here at some other forms of notation. Small case n is the number of data values in the sample set. Capital N is the number of data values in the population. And mathematically, we represent this as x bar. The sample mean is the sum of the sample values divided by the number of data points in that sample. And then mu is the number of value, is the sum of the values divided by the total population. This kind of notation is used to help us remember that we're talking about a total population as opposed to a sample of that population. So if we take a look at one calculation is related to our chocolate chips, it's kind of silly. I think you understand this. The median, however, is really the middle value, and meaning that about half of the data values are less and half are greater. The more precise one is that the data set is the middle value of the original data values when they're arranged in some order, increasing or decreasing magnitude. So when we are looking for the median, we often put the little squiggly line that's associated with the Spanish ñ, but it's called, that symbol is called a tilde. So we pronounce this X tilde. That tells us that it is the median of the sample, okay? In other words, it's exactly in the middle. So if we look at this here, the 5 samples that are in the previous example of an average of mean, we had 22, 22, 26, 24, and 23. If we put those in order, 22, 22, 23, 24, 26, the middle value is 23. Note that we do not calculate anything around that. This is meaningless that the data spread is higher than the median. So you can see that it doesn't matter here that there could be a number way out here if this is the median value. And what that means is that this value is what we call a resistant measure of mean, meaning that extremes don't have the same effect. It's not to note that it doesn't have any effect, but the effect is not mathematical, it's positional. So we can do that with anything. Anytime we have, by the way, if we have 6 chips, so the median is going to be halfway between the third and fourth. So we simply take the mean of those 2 middle numbers, the average. So the median of this one is 23.5. Well, it's not likely you're going to have exactly 23.5 chips in a cookie. So, but that is the median. We don't like the word average for mean, and we're trying to make sure that that we understand that there is a little difference here. Although, as I said, in Excel, the statistical functions, and we'll call up Excel in a bit and look at those the statistical functions, then what we find is that they use average as opposed to mean. Mode, we talked about. It's the value that occurs with the greatest frequency, the most number of times. And we can have multi-modes of the data set. So the mode of the chips that were used in the first example, there were 5 chips, 22, 26, 24, and 23 chips. So the mode, there were 2 occurrences of 22, so the mode is 22. If there is no value that is repeated, the set has no mode. Mid-range is basically, it's another measure of center that can be used, but it's a value that is exactly halfway between the maximum and minimum values of the data set. So if we are looking at that, again, going back to our chips, we've got a data set that runs from 22 to 26 chips. So we add 22 and 26 to come up with 48. Divide that by 2, we get 24. With a small enough set, that's a real quick mid-range that doesn't require a whole lot of calculation other than knowing the maximum and minimum values. There are some round off rules, just basically one more decimal place than is present in the original set of values, which is why this is 24.0 as opposed to 24. So we find we want round only the final answer. So we don't round any of the any of the components until we get to the last example. In fact, in most of math, it's considered appropriate to not do your rounding until you've done all of the calculations. So we can look at it that way. There are examples of times when we don't have any meaningful use of such things. Zip codes. So what? I mean, the zip codes, you know, there is no meaningful analysis you can do on zip codes or on the jerseys of athletes. So we talked about that as well. Class size. It is well known that smaller class sizes are more effective. According to the National Center for Education Statistics, California has a mean of 20.9 students per teacher, and Alaska has a mean of 16.8, based on elementary and secondary schools only. If we combine them, we might find the mean number per teacher of 18.85 as the calculation shown below. Notice this is carried out 1 decimal point further than what's in the basic data. This is a not useful number because it doesn't take into account the vastly different number of students in California versus Alaska. So we're comparing apples and oranges, and to just compare them straight across means nothing. This is another misuse of statistics, and so you can't really use such things. Very, very different sample sizes, the numbers they give here. If we combine California and Alaska, we get 6.5 million students and 315,000 teachers. So that ratio is 20.8, which is not appreciably different than the California number, which tells us only that California has significantly more students than Alaska, something we already knew. We have, going back to these, looking at the IQ scores in our low lead group that we looked at the other day. We've got lots of frequencies, and we've got a midpoint. What do we got here? All right. Hang on a sec while I check on something. All right. All right, forget that. So we look at our class midpoint, which is X. Remember, we had frequency distribution and classes and stuff. And we have these frequency distribution issues. First, multiply the frequency, each frequency and midpoint, and add them up. So this is the sum of the frequency, which is the number of appearances of students in this in any class, times the class midpoint. We get a lot of values. So we sum those up, and then we add up by and then sum up the total number of appearances, the frequencies. So we're dividing this number 7,201 by 78 to look at frequency distribution. And The frequency distribution issue, let's back up a page here. I want to go down here. The mean from a frequency distribution can be done as well. We do this by weighting each of those frequencies and then dividing. And so it's possible to do the weighting by looking at the number of appearances and the midpoint. Well, the midpoint is sort of a measure of the mean of the 33 values that in the 70 to 89 range and the 35 and the 90 to 109 range. If we multiply that by the midpoint, we're going to get a number, and we'll get a number that gives us an approximation, but it's a quick means of looking at another way of looking at the center of a data set. Let's go on. So this is what we call a weighted mean. We have a weight, and then that's the basis for that. The weight in this case is the number of units in there, and the value is the midpoint, and then the sum of those weights can be done. So this is how grade point averages are computed. We can do a nice long calculation. So we've got we have these letter grades, A, B, and C. We have D's and F. So we have, if we have replacing the letter grades A, B, C, and D, we've got 4 and 4 and 3, 2, 0. Now use that formula, and what we've done is using the number of credits for each course, with 1A was in a 3-credit course, a B or an A was in a 4-credit, etc. So we multiply all these things out, that weighted average. The student who got an A, B, C, and F has a weighted average of 3.07 for his or her grade point average for that semester. Obviously, the F pulled it down, but not by a whole lot. The F, the class, the F was in a 1-credit class, so it didn't pull it down by much, but it was still a 0. So we have lots of ways of calculating these things. Let's not mess with Minitab. Okay, keep on going. Keep on going. Measures of variation. That's the thing I want to get to next. Variation. Variation is something that we look at quite often in our statistics, because variation is really the spread of data. So let's go ahead and take a look at some chips here. And he's made up some chips that he has proposed that he makes, where his chocolate chips were distributed from 23 to 25 with a mode at 24. And so we have that. But looking at the Chips Ahoy regular, they run from 19 to 30. 19 to 30. And so this is a very compact data set. This is a spread out data set. Both of them can be looked at as relatively normal distributions. So the ranges we can calculate for the Triola chips are 25 minus 23, or 2. The range for the Chips Ahoy are 30 minus 19, or 11. So the range is different. The midpoint with the Triola clearly is 24. The midpoint with the Chips Ahoy are 19 plus 30 is 49, divided by 2 is 24 and a half. So the midpoint for the mid-range, it's halfway between these two in this example. So it too is not terribly useful, but nonetheless we do have those. So let's take a look at standard deviation. It is probably the most common measure that we calculate in statistics. Standard deviation is really a measure of how much data values deviate away from the mean, either positive or negative. We can have, and we calculate a standard deviation by a couple of different means. If you were doing this on paper, you would add up the difference between the mean and each data point squared. So you would calculate each data point and the difference between each data point and the mean, and it's squared because we can have negative values in the data of this. The difference between x and x bar can be negative, but when you square it, of course, it becomes positive. You remember that from your algebra and other math. So we end up with a positive number. Sum all those squares up and divide by n minus 1. Now, we calculate n minus 1 because the reasoning is that that we are looking at one of those points is going to be right at the mean. So we're really looking at those that are away from the mean. And so it's going to be n minus 1. This other formula is the formula that Excel and calculators such as the TIs and so forth, the big Casios, use to calculate. If you were doing this by hand, this is what you would do. You could do this, but it's more work. It's easier for the computer. So what we have is using that formula. We go back to the cookies, go back to this 22, 22, 26, 24. Those are the first 4 chips. There's 40 of them. Here is where we want to use this is where we want to use Excel. Standard deviation of a sample is denoted as S. The standard deviation of an entire population is noted as small sigma. And we'll get back to what that difference is there. The biased estimator is one of the reasons that we do n minus 1. If we're dealing with an entire population, we use n. The calculations are the same. The only difference is that we use n instead of n minus 1. So we compute the mean. So we've got 22, 22, 26, and 24. That adds up to 94. So the mean is 23.5. Subtract the mean from each value. We get minus 1.5, minus 1.5, 2.5, and 0.5. So the square of each of those deviations, then we calculate those. 2.25, 2.25, 6.25, and 0.25. Then add them all up. This gives us 11. So then we divide by 3, which is the 4 data points minus 1. 11 divided by 3 is 3.6667. Then we find the square root of that. The standard deviation now is 1.91 or 1.9. Since we only have even numbers, whole numbers of chips, we only use 1 decimal point. So it's 1.9 chips is the standard deviation. What this means is that most of our data, and this is the important part about standard deviations, in a normal distribution and in a large enough data set, we expect normal distributions. Standard deviations, the 67, I think, % of the data fall between -1 standard deviation and +1 standard deviation. So if the mean of our chips were, here, 20 with 23.5, what we're saying is that 67% of our data would fall between 21.6 and 25.4 chips. Obviously, with this few samples, that's a sort of a meaningless number, because if we add in some more chips, we're going to get in a different number, slightly different number. This is just showing that you can get basically the same number by calculating using the method that is used in that's in the computer. So it gives you the same number. It's just a little more cumbersome in my book. We can compare data sets of different standard deviations, but it's not a good idea to compare them when they're very different. Very different standard deviations means your data set have very different distributions, and it's not, statistically, it doesn't make sense to compare samples with very, very different numbers of, in terms of standard deviation. If we compare all of the chips in the Chips Ahoy with 40 of Triolas here, what we're going to get is a standard deviation. And again, we calculated 1.9, but if we include all the chips, we're going to get 2.6. Triola's chips, the difference, remember, it was a much more compact. The range was only 2. Standard deviation of 0.07. So when looking at comparing standard deviations when the sample means are approximately the same. So the standard deviations can be compared. What we're saying is that Triola, at least fictionally, has a much more rigorous quality control system that will give him very much the same chips to his cookies than Chips Ahoy does. We'll get to something called the coefficient of variation in a bit. Rules of thumb. Remember, we have a standard deviation. If we look at, there's something called a range rule of thumb. We look at the range. What we find is that, we'll get to a little bit more about this later. I mentioned that 67% of data sets fall within 1 plus and minus 1 standard deviation. Turns out that about 95% fall within 2 standard deviations of the mean. We can look at something we call the range rule of thumb, which is a very quick way of determining an approximate standard deviation, which is to divide the range by 4. Remember, the range is the minimum and the maximum plus and minus 2 standard deviations. And so basically the minimum and maximum are approximately equally distributed, and our standard deviation 95. So we're going to get 95% of our data in this range of plus and minus 2 standard deviations for a total of 4 standard deviations in the standard deviation ranges. So if we do that by calculating the range and then divide by 4, we're going to get an approximate standard deviation. So again, as we remember, in the 40 cookies, we had a range of 11 and a standard deviation of 2.6. If we look at the range as the maximum and the minimum, so we've got 30 minus 19 is 11 divided by 4 is going to be about 2.9 or 2.8. Let's see. Yeah, 2.75, so 2.8. Whereas the calculated value was 2.6. All this is good for is giving us a rule of thumb for what that standard deviation. And we can use that to determine whether the cookies that are outside the range are plus and minus 2 standard deviations from the mean. So we have we already know what that mean is. We have a 2.6 standard deviation. When knowing that what this is, we can the mean being 24. If we use the 40 chips of regular, we got 24 as the mean. Standard deviation is 2.6, and using the range rule of thumb to find the minimum and maximum usual numbers of chips. Okay, so the minimum is the mean minus 2 standard deviations. Okay, so that's the range here. The minimum of that is the mean minus 2 standard deviations, or 2.4 minus 5.2, or 24 minus 5.2. So we get 18.8. And the maximum usual value, and this again, these are approximations. What we take here is the mean, and then we add 5.6 or 5.2, we get 29.2. Well, 30 is above that, so we can consider that to be an unusually high number. 19 is higher than this minimum value, so we can consider that a normal range. So we have one value that appears by this rule of thumb method, just sort of an inspection here, to be outside the range. So again, using this estimation here, as I said, the estimation of the standard deviation is 2.75 if we use the range. It's quite close, but it's only based on the minimum and value. So it's a rough estimate that could be off by an amount. If we're looking at a population, we use slightly different notation, but we divide by n, because when using the entire population, we have reduced the bias that comes from using only a sample. Variance is another term we use, which is also spread, and but the term variance is something that we calculate. It's a set of values which is equal to the square of the standard deviation. In other words, it's this calculation here, or x minus x bar over n minus 1, before we take the square root. Variance is a resistant form of looking at variation in the population. So the importance here is that it's an unbiased estimation of the population variance of the sample variance is an unbiased estimator of the population variance. So we're not going to worry about that any further. So we have variation here is a case of we're not going to worry too much about some of these things here that we call like mean absolute deviation, which is really the sum of the differences between each data point and the mean divided by n. In a large enough data set, this is going to be 0. So that's why we use the square. So we're going to just keep on going. Dividing by n minus 1, there are only n minus 1 independent values, meaning we can only freely assign any number before the last value is determined. So we won't worry about what all that means. But let's take a look at what we see here. This is our standard bell-shaped curve. It is what we call a normal distribution. It's centered on x bar, the mean. So I was wrong. It's not 65. It's 68 or 67. It's 68% is within plus and minus 1 standard deviation. 95% is within plus and minus 2 standard deviations. What we say is that the usual data, usual values, expected values of data fall within 2 standard deviations of the mean. So anything outside this 95% level is considered to be an unusual result of a measurement. Further out, we get 99.7% of the data are within 3 standard deviations of the mean. So the vast majority of data is really centered between 2 standard deviations plus and minus of the mean, and almost all the data are within 3 in a normal distribution. Normal distributions are expected when we are having a large enough data set. We can have very different results when we have data sets that are very small. So that's why we like larger data sets. We want to have what we call statistical power. Different populations, if we're looking at different populations and we're comparing variation, what we want to do is look at, and this especially is true when we have very different standard deviations, but the same mean. If the means are different, if we can't really compare the data sets other than to look at what we call the coefficient of variation, which is to divide the standard deviation by the mean. And that gives us an idea of how the data sets compare. So we can take a look here at two very, very different types of data sets. One is our Chips Ahoy, our favorite chips, and then the weights of regular cans of Coke that are listed elsewhere. We won't go there, but using sample data, we have the results. The cookies, we already know the mean is 24, standard deviation 2.6. Coke has a mean weight per can of 0.81682 pounds and a standard deviation of 0.00751 pounds, which is how do we compare these two different data sets? And we do this with the coefficient of variance, coefficient of the coefficient of variation here by dividing the standard deviation by the mean. So for Coke, the chips, the standard deviation was 2.6 divided by 24, or 10.8% standard deviation. That's the coefficient of variation. Coke, much more compact, a standard deviation of 0.00751 divided by X bar, the mean weight in pounds, we get 0.9%. So we can't compare standard deviation of the chocolate chips to the standard deviation of the Coke cans, but we can see, we can compare the coefficients because they don't have units. We've divided 2.6 chocolate chips by 24 chocolate chips. There's no units, and pounds by pounds. So what this says is that if you were looking at quality control, the quality control on the packaged material in cans of Coke is much more tight than it is in chips in the Chips Ahoy chips, for whatever that means. So you'll be calculating some of those values. So it's now 7:45. I'm going to see what's next here in this chapter. Keep going. We'll come to this later. We've got box plots, which are, and we're going to be looking at something called a z-score. It's a standardized value, which is the definition of a z-score is the number of standard deviations that a given value of X is above or below the mean. It's basically how far away from the mean is an individual data point. So we're going to cut that off here. I'd like you to get started on some of these other issues here. Let's just make sure that we are looking at what I want to. Yes, we are. Okay, close that. So here we are. Oops, let's open you up again. So I'd like you to get looking at the discussion and remember the discussion is about which central measure of central value of a data set would fit in one of these scenarios. Okay, so again, this is a 300 course. So 200 plus words and at least two references properly cited in text. You can start looking at some of the material in the assignment. I'd wait on the assessment for later. So that's as much as we're going to do tonight. Go ahead, and when you see this, and I hope you can see it soon, send me an email, and the code word for this one is Mumbai, M-U-M-B-A-I. So if you can send that code word to me in an email, that lets me know you've watched this, and everybody's going to be happy. So it's now approaching 8 o'clock, and it's about time for the power hour to begin. And so go ahead and get started. Again, always, when you, if you have questions, email them to me, and I will look forward to seeing you on Thursday. And again, I'm very happy that no one was hurt in your little prang, and hope you can get your truck on the road again soon. Anyway, we'll see you on Thursday, Jess. Bye now.